He talked about the science. I'm now going to talk about how we did this. I emphasize that although I am talking, I'm really doing so on behalf of a large instrument team. There are many people who have contributed to this, and I'm simply the one who gets to stand up and talk. As Steve noted, the underlying science motivation is to probe the dark ages, cosmic dawn, and the epoch of reionization, just as the first stars were turning on, the first accreting black holes, and really understand when and what the first objects were to light up the universe. Steve went through this plot in considerable detail. I would echo his comments that this is really just a way to set a framework to ask the kind of questions. And again, echoing what Steve said, at some level, in fact, perhaps taking what Steve said a bit further, I hope that what we find is not this, because that would be boring. The important thing would be to find something that the theorists didn't predict. But the notion is to go after turning points, Bravo, Charlie, and Delta. Those turning points, that was part of a mission optimization, or why those turning points, that was part of a mission optimization between what is already being done on the ground up at higher frequencies or lower redshifts, and what might realistically be accomplished in a reasonable mission duration. The motivating science then flows to a science instrument. DARE itself carries only a single science instrument. We can do this experiment with only one. It is a broadband RF radiometer, so essentially measuring power as a function of frequency over a fairly large band, 40 to 120 megahertz. It is important to think about the entire instrument as a whole, but for the purposes of illustrating the signal flow in this talk, I'm going to talk about three of the subsystems in it. There is the antenna itself, and then first the analog electronics, and then the digital electronics, an analog receiver, a digital spectrometer. There are, of course, other things like command and data handling and power, but those are fairly standard spacecraft subsystems, and I won't say anything more about those. An important aspect of the DARE science instrument is it has considerable heritage both from the ground and from space. For instance, one of the ground-based instruments that is currently attempting to measure the turning point echo, which is the highest frequency or lowest redshift measure of the epoch of reionization, is this experiment called the experiment to detect the global reionization signature edges. Here you can see it deployed in Western Australia with one of the PIs, Alan Rogers. The other is our colleague Judd Bowman, who's been very heavily involved in the DARE experiment. That's the ground-based side from the science. From the space, there's been a long history of putting up RF instruments or RF systems operating in kind of the comparable frequency bands. Thus, for instance, LANL has Forte, which is, I believe, still operational. NRL had STP-SAT with Citrus, this antenna here. And just to emphasize how long this heritage is, SOLRAD, I believe that instrument is about as old as I am. It is, of course, no longer functional, but the spacecraft, when it first flew, was about the time I was born. So there's a very long heritage of both ground and space-based observations at these frequencies. Okay, drilling down now into the instrument and thinking about the signal flow. The antenna is the first part of the first subsystem in the instrument. When the radio waves first hit the science instrument, it's actually two aspects. One is there's a pair of tapered biconical dipoles. That topology, that particular topology, was chosen because it's both low mass and compact, yet can cover the entire frequency range. There are other topologies, there are other designs that we could have chosen. For instance, something like the LANL log periodic, or the Forte log periodic, but those tend to be larger, probably higher mass, and importantly would almost likely require deployment, which would increase risk. And this design does not require deployment. The design itself can be constructed out of standard spacecraft components, a wire frame with some gold mesh. Gold mesh is commonly used, for instance, on communication satellite antennas. And then this support structure, this sort of honeycomb or lattice structure, is used to support it, as the name suggests, for instance, during launch. And that is, again, high spacecraft. It's been used many times on spacecraft or other planetary science missions. The other aspect, and this is the only deployable aspect of the entire spacecraft, are these radials, which form an effective ground plane, which means they end up pushing or directing the antenna power pattern more in a forward direction and effectively shielding the antenna somewhat from the spacecraft itself. You can see here, this is a model that has been run by our colleague Rich Bradley, who has actually been instrumental in designing much of the antenna. This is the power pattern as a function of both elevation or azimuth and angle and then elevation and angle. And you can see that the power pattern is very well localized and importantly is very smooth in angle, and I'll come back to that point. The radials themselves are very standard spacecraft equipment. They've been used, I've been told, as many as hundreds of times for deployment without a single failure, and I believe they've even been used on GPS spacecraft. So extremely high reliability. This is not only a PowerPoint antenna, there is actually already a prototype or proof of concept antenna that Rich Bradley has built. You see it here deployed essentially in his backyard, I believe. Constructed here, you can see the two biconicals, and the size is something like 1.2 meters. So it's something of order that size, and you can then judge from that how high it's standing above the ground. He's been connecting this to, for instance, spectrum analyzers or network analyzers and measuring various properties of it. Here you can see the reflection coefficient. And the important aspect, this is the amplitude and the phase, the important aspect of it, without going into any more detail, is that these are extremely smooth in frequency. If you recall the plots of the spectrum that both Steve and I have been showing, they are showing changes in frequency. What we are trying to find are those changes in frequency and where they occur, and then their amplitude give us an indication of what was happening in the dark ages or during cosmic dawn. It's extremely important, therefore, in thinking about the instrumental design, that the instrument does not introduce any kind of ripples or fluctuations as a function of frequency that might be confused with the kind of signal that we're trying to find. And what you can see is, at least from the preliminary measurements, these are extremely smooth curves as a function of frequency, which is an important requirement for the science instrument. The next step then is the analog receiver. This is now, again, somewhat based on lessons learned from EDGES. It uses some active elements which are designed to match the changes. Although the science antenna does have a very smooth frequency response, the frequency response is not constant as a function of frequency. So it uses some active elements to effectively match those variations in frequency. I won't walk you through the circuit diagram, but if you want to see it, there it is. One of the other very important aspects that we learned from EDGES was when EDGES deployed to Western Australia, or when they've deployed, what they've had is they've had an antenna sitting out, say, 100 meters away, and then essentially all the other electronic components sitting in some hut with a coax cable running between. And what they've been discovering is that long cable run ends up with essentially reflected waves along, or reflected signals along the coax cable, which introduces frequency structure. And as I said, we want to avoid that. Therefore, what we are going to do, in addition to these support structures, there's a central mass to hold up the antenna, and we're going to stuff some of these analog electronic components right up into that mass, effectively getting them as close as possible to the end of the terminal of the antennas as possible. The notion there is to remove that long cable run and thereby reduce, and we think we can effectively eliminate all of these reflections and which introduce frequency variations. In addition, we will be using a so-called, it's getting cut off here a little bit, a cylinder in a cylinder, or essentially a can in a can, keeping these analog components very thermally stable or very thermally controlled, so that as the spacecraft, for instance, goes in and out of shadow or gets different solar illuminations, the analog components are not going through large temperature variations, again, to try to keep them from changing their response as a function of frequency. This technique has been pioneered by JPL. It's not very well represented here, but essentially you take one cylinder which you control to some thermal level, and then you stuff another cylinder inside it, and because the interior of the first cylinder is already well controlled, then the second cylinder you can control even better, and we believe we can get it down to millikelvin thermal stability. Again, this is not only a PowerPoint receiver, there is actually a receiver being constructed at JPL to start testing some of these things. Here you can see the initial components being assembled on a lab bench, and this is in fact already undergoing some testing. Again, one of the important things of why we have to do this is as it was being assembled, there were some I think the phrase was interesting oscillations being seen that the team is trying to understand better. The next step then is the analog receiver hands off to the digital spectrometer. Of course, we have to go from analog signals, or we'd like to go from analog signals to ones and zeros so that we can analyze them with computers. The basic design is to simply digitize the incoming signal and then translate that or convert that to frequency. The frequency range implied by the redshifts of interest is 40 to 120 megahertz. I will not explain why we think we need a 10 kilohertz spectral resolution or frequency resolution, but let me assert that we do. And if you work out those numbers, that means that's something like an 8K point spectrum, which by modern standards is not at all difficult. The difficult or the challenging aspect is that the signals of interest are something like 10 to the minus 6 times smaller than all of the other foregrounds. If you look at the sky, for instance, here's a map of the sky at 45 megahertz, so at the lower end of the DARE frequency range. Effectively, the power that the sky produces, or that the sky is providing to the antenna, is something like 1,000,000 times stronger than the signal of interest, or if you prefer RF units, 60 dB stronger. And what that means is that it actually does stress some aspects of the ADC, and this is in fact a challenging or cutting edge aspect of understanding how to do it. However, one of the other important aspects is at least what we are seeing, and I'll show this in a minute, but at least what we know today, there are rad tolerant both ADCs and then FPGAs that can be used to form the filter bank or form the spectrum. Again, there are rad tolerant ADCs and FPGAs have already flown on spacecraft, so there's a high heritage of the components that can be used for this, and it's just a matter of making sure that they actually will perform up to our requirements. Interestingly, as we were going through the mission design, one of the limiting factors actually does end up being the downlink rate in terms of capturing the data and getting it down, because forming an 8K point spectrum, again, at something like 1 second resolution is not a limiting factor. We could in fact produce it even faster than 1 second, but getting it down to the ground is a challenge. And again, this is not only a paper digital spectrometer or PowerPoint digital spectrometer. There's actually a group that has been injecting a weak signal into a reference spectrum. They're doing it from the standpoint of understanding some atmospheric experiments or understanding atmospheric observations from space. In their case, they have a 40 dB difference between, or essentially a 10,000 time difference between the signal of interest. It's effectively 10,000 times weaker than all of the other atmospheric foregrounds. But what they've been doing is injecting this kind of signal and then seeing whether the ADC somehow distorts that signal. And what their initial understanding is that it is not. And you can see here an example after about 150 hours of straight integration. I actually won't have much time to discuss calibration. It's an important aspect. Again, the idea is we want to understand the instrument very well so that we don't confuse any aspects of the instrument with the signal of interest. But again, we are very much being led by or learning lessons from edges. I've already indicated some of these. One of the important aspects about the calibration, and it's very important to keep this in mind when designing these kind of experiments, is the difference between absolute and relative calibration. We don't necessarily need a very good absolute calibration of exactly what is the power being delivered, but we really want to be sure that, for instance, if we say the power at this frequency is some value, that the power at a slightly different frequency, we have high confidence in what that is and that the instrument is not introducing some kind of variations. Again, I don't have the time to go into it, but the receiver itself is actually being designed. You probably can't tell, but there's actually 3 input receiver. There's an input port for the antenna itself, but then also two loads within the spacecraft that we can difference, and I've left off all of the equations, but by having that 3 input system, we can pull out what the power is from the antenna. And then finally, one of the other aspects, if you look at this map of the power on the sky, you can see that it is not uniform. Importantly, the signal of interest, these hydrogen signals that we're going after, they should be uniform on the sky because the universe is homogeneous and isotropic. And therefore, we have an additional lever or an additional piece of information that we can feed into the analysis method that the sky should vary as a function of position, but the signal of interest should not. This is the penultimate slide, and I hope you can't read it. This eye chart is largely an existence proof to show all of this is being done in the context of all of these previous pictures I've been showing of the antenna and the receiver is being done in the context of an instrument verification plan. It's perhaps been clear that I've been stressing the individual components are actually at very high technical readiness levels. They've all, in some cases, flown multiple times. But if you then look at assembling them into the actual antenna or into the actual receiver, we can't point to an actual antenna or an actual receiver of exactly our design that has ever flown before. So we need to take these individual components and verify that in fact they work together in the way that we need them to work, and advance that to effectively a high technical readiness level. Ultimately to the point that we intend to deploy a DARE-like antenna to Western Australia to verify its performance. Thus, that's the last slide, and I hope I've convinced you that not only is this of theoretical interest, but it's actually technically feasible, and we're actually starting now.
Thanks, Joe. Unfortunately, you've essentially used all your 15 minutes, but one very, very quick question if there is one.